Okay, today we're going to talk about different trends or patterns that you see on the periodic table. And we've learned a few already because we've done the electron configuration. So we see like all alkali metals end in S1, all alkaline earth metals end in S2. And those are going to give the characteristics for the atoms, or I should say pretty much the atoms or their ions. And we've learned oxidation number, that's a trend. We've learned the dot diagram, that's a trend. So we're going to see, there are several, but we're going to do three of the main ones. So I just want to say there are others, but we're going to show you three main trends. And most of these trends are based on the fact of their electron configurations ending the way they do. And so the first trend that we're going to study is atomic radius, and then we're going to talk about ionization energy, and then electronegativity. Some other trends would be like electron affinity, but we're not going to basically cover that one. There are several trends that we could do, but we're going to stick with these three main ones. So atomic radius, just like you think of a radius of a circle, that is the distance from the center out. And so it's the distance from the nucleus, that's where the center of the atom is, to the outermost energy level. So just like you would think, again, a radius of a circle. So basically the size of the atom. And as we learn these trends, we are going to talk about the most typical. You can Google and you can look at some periodic tables, and you're going to see there's going to be some exceptions, because unfortunately there's always exceptions. So first thing we're going to talk about, as you move down a group, you're going to see that the atoms are going to get larger. So as you go down a family or as you go down a group, you're going to see it get larger. And this should make sense because as you go down, if you think of us writing that electron configuration, that principal quantum number is changing. And that principal quantum number is the energy level number. And so it's an S1. 1s1, 2s1, 3s1. So the atoms are getting larger because we are basically adding energy levels. So if we were looking at a periodic table and we wanted to know which is larger, a magnesium atom or a strontium atom, well, strontium is going to be a larger atom. Notice there's that principal quantum number there. It has 5 energy levels as opposed to magnesium that only has 3. So it would make perfect sense to us that that would be a larger atom. So even if we were way over here and we had oxygen versus francium, francium is the biggest atom we've got there, and it's got 7 energy levels. Little oxygen only has 2 energy levels. So as we move down, the size of the atom gets larger. And again, that should make sense to our brain. What kind of doesn't make as much sense to our brain is the next trend. So that's the trend in a group. Well, there's a pattern. So as a group, the radius, let me go to white here if I can run on the black. Whoops. So as you go down, it is larger for radius. But what we're going to see is on a period. So what if they have the same principal quantum number? What would be larger? And so if I were comparing, let's just go smaller because I'll draw here in a moment. If I were comparing a sodium atom to maybe an aluminum atom there, our brain would tell us, well, this has got 11 protons, and this has got 13 protons, same number of electrons if we're doing neutral atoms, and our brain would say, well, that was a bigger atom. But it weighs more, but it actually is not larger in size. The pattern is actually this direction. As you move on to the left, the atoms are on the left in the same period are larger. They're less dense. They're more dense as we go over here. And if I were to draw some sort of illustration, and we already know that I don't draw well, but if I did that sodium, it had 11 protons. Now it has neutrons. Again, neutrons are good for nothing but adding weight to the nucleus. So it would have 3 electrons, right? So it'd have those 3 energy levels. I won't draw the electrons. So it has 3 energy levels. Well, I kind of want to do all the electrons. This is that old Bohr model again. We'll just must put that one there. So then it has a valence of 1, has 3 energy levels, nice and not so even there. And so this is sodium. And then if we have aluminum, so aluminum, sorry, I was going to do protons. Aluminum has 13 protons. This is aluminum we're about to draw. And of course it has some, again, neutrons in there. This has neutrons as well, but again, they don't have a charge and they're in there just to make mass. So 3 energy levels as well. They got 13 electrons. Let's see if I can do this where it looks smaller. I don't know. This one's supposed to be smaller than that one. I don't know if it really looks that way, but use your imagination. Okay, so here's what's happening is this, again, those 3 energy levels, they both have 3 energy levels. But this is 11 protons in the middle that are pulling in those energy levels. This is 13 protons pulling in those 3 energy levels. So this one's going to pull it in tighter. It's kind of like a magnet situation. This has 11 magnets kind of pulling inward. This is 13. So it's going to have a stronger inward pull, a stronger, we call, nuclear charge. And so it's going to make it a more dense atom. So on the periodic table, as we go to the left, and then again, this is the rule we would use if they're sitting in the same period as one another. As we go this way, they are going to be larger because they have less protons to pull them in. They have the same amount of energy levels. All right, let's go back to that periodic table then. So now if I'm comparing a calcium atom and a bromine atom, bromine 35 protons, this one's 20 protons, brain would tell us, hey, bromine is larger, but it's not. It's actually weighs more, but our trend is this direction, and calcium is actually a larger atom. And so as we move down and as we move to the left, we're going to see larger atoms. And that's what this is going to say. So atoms tend to be larger as you move left on the periodic table, as you move left in a period. Atoms that are in the same period, meaning the same row, they have the same number of energy levels. Atoms on the right, over here, have more protons in the nucleus. If they have more protons, that means they're going to pull to the center more, making it a smaller atom. So if you want to write this down, just pause, or you guys do have the PowerPoint put up for you. Okay, so down is larger to the left, so down and left are larger. Well, that's if we're talking about neutral atoms. So now we're going to talk about, well, what happens when they form those ions? Because we know that atoms form ions, and when they form an ion, they are charged particles. And we know there's 2 different types of ions. There's cations and there's anions. Cations are positive ions, anions are negative ions. So let's discuss what's going to happen to the size of the atom when we get a cation or when we get an anion. This is just a good little description. There are some exceptions in this, so if you were again to Google, you might find some little exceptions in here, but you can see for the most part we are larger here. Francium sitting down here is the largest atom. Most of these are rare, so that's why you're not seeing them. So, and this is probably really old. So, again, furthest as we go down and to the left. Well, this is what I was talking about, ions. What happens when we add or remove an electron? So here's my sodium atom. Sodium atom has 11 protons and 11 electrons. So they're nice and neutral, nice neutral atom. You can even see the radius. They measure the radius in picometers, or sometimes something called angstroms. So 186 picometers. And now, look at this. +1. How did it become positive? It's a cation, right? Well, it lost an electron. And when it lost that electron, it actually becomes a smaller atom. A couple reasons why. It loses an electron, so it pulls in tighter, but it's also where that electron's coming from. So look, now we have 11 protons, 10 electrons. We have more positives to pull in. Look at the radius. It's almost half. So cations are smaller because atoms lose electrons, pulling them in more. So I just want to show you because this helps. Understanding electron configuration helps a lot on this. And I really want to take a picture of that particular one. And it is it's doing what I'm telling it to do. I'm just not telling it right. Alright, so if I were to write that configuration out for that sodium, it would be 1s2, 2s2, 2p6, 3s2, no, went too far, 3s1 is sodium, it's 11. Okay, so there's the sodium guy. So it's got a valence of 1, forget a dot diagram. Its bigger energy level is the 3, right? So how did it get to this stage? How in the world did it get to Na plus 1? Well, we say it lost an electron. So where did it lose the electron? Well, it lost this electron right here. So if it lost that electron, you see now, we've talked about this. So this is not the atom anymore. This is that ion. It has the same electron configuration outer-wise as neon. It has lost an entire energy level. It's not neon because it hasn't changed the number of protons. So it still looks the same on the inside. It's just a charged particle, but it got smaller. So if cations get smaller, guess what happens to anions? You guessed it. They get bigger. So here's chlorine. Remember, chlorine was a smaller atom than sodium. So look at it, even looks smaller. Look, 99. Okay. 17 protons, 17 electrons, nice and neutral. We add one more electron, and it's not giving it another energy level, by the way. It's just filling up the energy level it has. But it's almost like the proportion from protons to electrons became too much, and it just kind of got too big, kind of got out of control, almost double in the size there. So if we do that configuration, we can see, and again, we want to practice because on your test you're going to have to write a configuration of not just an atom, but of an ion. So let's look, 1s2, 2s2, 2p6, 3s2, 3p5. That's this guy. So how in the heck did we get to this guy? Well, he's a -1 charge. So that means he gained 1 electron. So that means instead of being 5 here, it is now 6. That's this guy. Alright? That's that guy. So there's our configuration. I do believe that's argon. Doesn't change the argon, but it also makes the atom larger. So that negative makes that atom larger. And as we look at things in solution, and ions in solution, we'll be looking at why those atoms are larger than they originally were. So, anions are larger because they gained 1 or more electrons, making it less of a pull to the center. So those protons were pulling in 17 electrons. Now they're pulling in 18. So it got disproportionate. So it got to be a larger atom. So anions are larger, cations are smaller. And here's how you can look at it. So we got going on. So here's our original atom, and look at the cation. Original atom, and there's a cation. And you can see this is proportional pretty much throughout. Over here we get to those common anions. There's nitrogen. Here's a nitrogen 3-. Here's oxygen, an oxygen 2-. So you can see they're getting a lot larger, the green ones. The blue ones are smaller. And look, there's those transition. You're seeing those variety of oxidation numbers in that transition metals. Alright, that's pretty much for radius. So now we move on to ionization energy. So ionization energy, I'll write the definition and then we can see, is the energy needed to remove an atom outermost electron. So basically, how much energy does it need, another atom need probably to steal an electron from an atom. So basically, how much energy does it take to steal an electron? Think of it as theft. And if you think about the periodic table, who's got extra electrons and who's almost close to full. And if you think of it, those, for example, francium. Francium is a huge atom, bottom left corner. It's got one extra electron way out in the 7th energy level. It's probably not going to take much energy to remove an electron. In fact, the alkali metals, one of the reasons they are so reactive is because it doesn't take a lot of energy to remove their electron. Now you think of the noble gases. The noble gases have 2 in their S's and 6 in their P's. They're perfect. So it's going to take a heck of a lot of energy to remove an electron from a noble gas because, you know, it's kind of like they have the best security system possible. They got ADT, you know, you're not going to break in. It's going to take you a lot of energy. They got 5 locks on their door, etc. So it's the amount of energy basically to steal an electron. And so we're going to see ionization energy increases as you go up a group on the periodic table. And the reason is those atoms are getting smaller. And as those atoms get smaller, those electrons are getting closer to the nucleus. As those electrons get closer to the nucleus, it's going to take more energy to pull them off. For example, hydrogen. It's only got 1 electron, and it's really, really close to the nucleus. So it's going to take a lot of energy to remove the electron from hydrogen. So it has a high ionization energy. And it increases as you move to the right of the periodic table. And we already talked about on the far, far right are those noble gases. I will tell you the noble gases have the highest ionization energy, and so they'll always win in a competition. It's like if I'm giving you 2 elements and one of them is a noble gas, and I'm asking about ionization energy, which is the energy required to remove an electron, a noble gas is going to always win because, again, they have the best security system. So they're going to be the hardest to steal from. It's going to take you more energy to do that. So, and every time you take an electron away from an atom, it gets harder. Okay, it's going to get harder. I gave the analogy one year in my classes that our house got broken into. Actually, not our house, but our outdoor storage shed got broken into. We had a fence and we had a lock on our fence, but they climbed our fence. So it took a little bit of energy to get into our storage shed, but we didn't have our storage shed locked. Okay, and so they were able to steal a weed eater from us. Well, now we've got a lock on our fence and we have a lock on our storage shed. So anybody wanting to break it now, it's going to take a lot more energy. So every time you take one away, it's going to get harder. I want you to keep that in mind. So anytime you take one away, it's going to get harder. The atom gets smaller. It's going to require more energy. Okay, so this is just showing the trend. Look how high hydrogen is. Hydrogen is going to be high because you only got that one. But look at this. Those noble gases, man, they win. Again, the trend is mostly this way. I don't know, can't really explain. We do have some exceptions going on here. So I don't want you guys to worry about the exceptions because there's charts. If we really wanted to know, we're just trying to get the overall trend. So we're saying up and to the right for ionization energy, and we do have some exceptions going on here. Has to do with that half-filled thing we talked about. So that's partly what's going on with that. So don't worry about exceptions because now you can see if we really truly want to know, we look them up. As you can see, a little exception going on there. So we're looking for that overall trend. It's who would have the highest, and you can see those noble gases are going to always win. So the overall trend is up and to the right for ionization energy. So this is what I was talking about, the stealing, getting harder. Ionization, i.e., generally is measured from 1 electron at a time. So to take the first one off, it's going to call the first ionization energy. To take another one off, it's called the second ionization energy. To take a third, it's called the third ionization energy, etc. And it's going to go up. That number is going to go up because it's going to get harder. So first ionization energy required to remove the first outermost electron. I had to add that word outermost because students were saying first. First would be the one closest to the nucleus. So I want to go first would take a lot. First, outermost. And every time, it's going to get harder. The atom's going to pull the electrons in closer. It's going to require more energy. And so this is the way we're going to use it. It says, this is how they know oxidation number. If you ever wonder, how in the world do they know oxidation? This is how we determine the oxidation number for cations. We actually use something called electron affinity for anions. We're not going to do the anions. We're just going to do the cations. But they look for large jumps in the ionization energy to help us predict the oxidation number. So I'm going to show you a chart, and then I'm going to show you how it would be on your test. Okay? So here's a chart. And what you're looking at is a bunch of ionization energies, and so you can see your sodium, magnesium, aluminum, silicon, phosphorus, etc. And so this first column is the first ionization energy, second, and then we've got third, fourth, fifth, sixth, seventh. So this would be to take the one electron away. And after you take the first one, this is take another one away, third, etc. So just look at sodium. We already know these oxidation numbers, but I'm going to just walk you through several of them, and then I'm going to show you how it would be on your test. So this is kilojoules per mole of energy. Okay. So to take one electron away from the outermost electron from sodium, it's going to take 496 kilojoules of energy. And most of you know I used to teach high school, so I would always give the analogy of money. So, because when you relate to money or food, things make sense to us. So let's say you wanted to buy a new cell phone, and you say, hey, to buy one cell phone, it's going to cost me $496. Okay, so to get one. Well, to get a second one, I should say, not to get two, but to get a second one, it's going to cost you a little bit more. Because, cell phones are getting hard to get. 4,560. Is that reasonable? Probably not reasonable. See that huge gap in those numbers? This one's not reasonable. And this is why we predict that sodium will have a +1 charge, willing to lose one electron. Probably not willing to lose second. See the large jump? This is what that's referring to. Here's magnesium. Now it's going to take more, because you think, look where he's on the periodic table. It's a smaller atom. It's going to take more energy than it did sodium. So 738 kilojoules of energy to remove his outermost electron. So one of those S's. To get a second one, it's going to take 1,450, because remember, as you take that one, it got smaller. So it's going to take more energy to get another one. But that's kind of reasonable. That's reasonable. So about double that. Look here, to get third, now we're getting into a whole different energy level. If you think about where we are and what we're doing when we're taking those electrons away, to get to another energy level, now it's going to take 7,730. That is not going to happen. So that's why we predict that this makes a +2 charge, or a +2 ion. Remember, you can also write it like this. In fact, you're going to probably see it written like that more than that. I just have gotten in a habit of putting +2 back from my algebra days, so that's probably the better way. So it's going to make that kind of ion, a 2+ ion. All right, aluminum, and then we'll move on. So 578 to take away 1, 1820 to take away 2. That's a pretty good jump. 2,070, pretty good jump, about 900 or so, a little less than 900. Look here. That is a little less than 9,000 jump there. Not happening. Of course, this little thing makes it pretty obvious, right, going down there. And so that's why we predict a +3 charge, or a 3+ charge on aluminum. So we use that. Well, because I've showed you the trend on the periodic table, I'm not going to use numbers like that. I'm going to give you element X, and you're going to predict, and that's what you're going to do on the worksheet, you're going to predict the charge of element X. So for instance, I would say it has an ionization energy, a first ionization, we'll just go like this, ionization energy first, second, third, fourth. And I'll just make up numbers. I don't know. I don't have any rhyme or reason on them. So 300 kilojoules per mole, about 620 kilojoules per mole, and then maybe 5,922 kilojoules per mole, and then probably about 11,200 kilojoules per mole. So probably reasonable, huge jump, not going to happen. So we would predict a 2 plus or a +2 oxidation number for this mysterious element. Give you one more example. Still element X. I think on your worksheet I did 1, 2, 3, but we'll just use element X. So let's say it's going to take about 700, sometimes that board does that, 700 kilojoules for this guy, and about 13. Where's that big jump? Well, the jump's here, so this one's not going to happen. So we predict a +1. Okay, so I'm just going to make up numbers, because if I gave you real elements now, we could just look at the periodic table, because we could do that. I guess I could use some random transition elements, but I think you get the idea of how we use ionization energy. There's another whole trend called electron affinity to anions. These are for cations, because the definition is the amount of energy to remove an electron. So we use those ionization energy to predict oxidation number for cations. All right, so now last trend. Well, last trend is electronegativity. So electronegativity we'll be using a lot because we're heading to bonding. And so electronegativity is when two atoms are in a bond with one another. They are basically having I love this illustration, they're having a tug of war with the electrons. And it's basically which atom will pull electrons more towards it. Okay? So basically which one's more stingy with his electrons, which one's going to pull harder to get the electrons to come closer to it. And so I love this illustration. So if you can keep this illustration in your head for electronegativity, it's going to help you a lot. So if you think about it, I don't know which one of these guys you think it looks a little bit stronger, but I'm going to say this one looks a little bit stronger. I'm going to let this one be fluorine. I'm going to let this one be sodium. I think I'm, yeah. Alright, so I'm going to have a bond between sodium and fluorine. Okay, so they're playing a tug of war there. This is sodium. Here, I don't have a shirt for them. That's sodium. Doesn't work really well with it. Red. That's fluorine. Okay. So as they're having a tug of war, well, you think about this one. It's almost full. It's at P5. So, and it wants how many in its valence? It's got 7 in its valence electrons. How many does it want? It wants 8. So do you think it wants it? Oh, it really, 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 really wants that electron. It's so much that I probably should have picked something that wanted 2 electrons since there's 2 sitting there. That's okay. So it really, really wants that electron. And it's so much that it's going to pull that little electron towards it. And this guy's just going to look, it's got this little extra one. And because it's got that little extra one, this one's going to lose it and become positive. And that electron's going to go that direction. This guy's now going to become negative. And look, we talked about this in class. That's going to become a 6. Right now we got a -1. And this is what we call an ionic compound. And that is when one electron basically pulls an electron off of the other. I really wish I would have done with 2. But that's okay. We're just going to use 1. That guy's just going to have to go away. So this is illustration of an ionic. An ionic means that they're going to actually pull that electron completely off of that based on the electronegativities being so different between those two. Now, if those electronegativities are a little bit closer and we didn't have someone so stingy, sometimes they will play tug of war and they will not let go. Have you ever played tug of war with someone? If you've ever played tug of war, there's different types. You know, if I'm playing tug of war with someone really like a big old football player, I'm going to be like an ionic bond, and I'm just going to let it go. Okay? And that's what happens in an ionic. One just lets go of the electrons, and the other one takes it. But if I'm playing against, like, my husband, now he's stronger than I am. Okay? But I'm bound to determine I'm not going to let go of that rope. And so he's a lot stronger than I am. So he's going to pull those electrons closer to him, but I'm still going to hold on. And we are going to call that a polar covalent bond. So meaning I still have hold of the electrons, and that means that we're going to share those electrons, and I'm going to pull them back towards me occasionally, but he's probably going to pull them more towards him. Now, if you're playing tug of war with someone maybe more equal your size, like my daughter's probably closer to my size, and we probably don't really care enough to play tug of war, but we would see those electrons kind of go back and forth, back and forth, back and forth, and that's going to be called a nonpolar covalent. What that means is we're going to see that we have an equal sharing of electrons going back and forth. So let's look at this. So the trend. Metals have low electronegativity because they have those extra electrons that they're willing to give up. That's why they make cations. Nonmetals are high electronegativity because they're almost to that noble gas configuration, so they're going to pull those electrons really close to them. So the trend seems to be, as you move to the right and as you move up, same trend that we see on ionization, up and to the right. Fluorine is the most electronegative element on the periodic table. Now if you think about it, wait a minute. That's not the element that is further up and to the right. The furthest up and to the right is actually helium. The definition of electronegativity is an attraction for electrons in a chemical bond. Noble gases don't have an attraction for electrons. They don't get involved in a chemical bond, so there is no electronegativity for noble gases. So the last little thing, noble gases are not included because they don't have attraction for electrons. So fluorine is the most electronegative. Oxygen, nitrogen, chlorine, also very high values. We're going to see, for our purposes, nitrogen, oxygen, and fluorine for something we're going to learn very soon when we do another trend. Oh, why are we not clicking? Alright, so here you can see, here's some values. They measure it on like a 4.0 scale. So look at francium. Definitely willing to give away its electrons. Not very electronegative whatsoever. Look here. 4.0, highest guy on the periodic table, 4.0 there. So these are how we measure their electronegativities. And what we do with these to determine whether or not something is going to fall, whether we're going to play tug of war and they're going to let go, meaning the difference is so great one's just going to let go, or whether they're going to pull back and forth not even, like me and my husband, or whether they're going to pull pretty even, is we take these numbers and we subtract them. So for instance, most of us know that this is an ionic compound, right? So what we do, and you always take the big number minus the small number, you always take the most electronegative minus the least electronegative, or you could just say take the absolute value after you subtract. We've talked about that before. So if I have sodium chloride, which is ionic, by the way, and I subtract their numbers, the most electronegative minus least electronegative, and we always put them in order of least electronegative to most electronegative. That's why the metal always gets written first. So we're going to take 3 minus 0.9, you get 2.1. So I'm going to show you what we do with this number in a moment. So if I subtract those two, where this number falls tells us what type of bond is occurring between those atoms. For example, an O2 molecule is an oxygen bonded to another oxygen. Well, that's 3.5 minus 3.5. We'll get 0. What we're going to find with that is what we call a nonpolar covalent. They're going to tug back and forth, but they're going to be very even. So they're just going to share those electrons back and forth, back and forth, back and forth. Okay. So let's get to electronegativity. Up, I have that off a little bit. Up and to the right, stopping right here with fluorine being the highest, we are going to exclude the noble gases. I had a student make up this one for the electronegativity. It excludes noble gases. So that way you can remember this family does not count in this trend. Again, because it's an attraction for electrons, there is ionization energy, because that's the amount of energy it takes to steal, and ooh, it takes a lot for them. So highest ionization energy, but no electronegativity for noble gases. So here's what we do. We can subtract the differences in the electronegativities to determine if a bond is ionic, polar covalent, or nonpolar covalent. So if the difference is 1.7 or greater, what was ours a while ago? 2.1. So that's greater than our bond between them is ionic. What that means, again, is one is going to completely steal the electrons from another. They're not going to hold on. Think of the tug of war. It would be like me letting go of the rope. And then if the difference is 0.3 to 1.69, that means they're going to share. One's not going to let go of the electrons, but it's going to be an unequal sharing. It's going to be like, an analogy I gave is we bought a Wii for my children once, and the thought was that they were going to share it fair, but my son ended up kind of taking possession of it. He let her play occasionally, but it kind of hung out in his room. So they were still sharing, just not equal sharing, which is what we call polar covalent. The reason it's called polar covalent is one becomes slightly negative because it has the electrons more often, and the other becomes slightly positive. But it's not like the ionic, so there's more of a positive negative side to the molecule. The electrons again are going back and forth between the two. If we subtract and we get a difference, remember the oxygen, our difference was 0. We have a very even sharing going on, and we say that's nonpolar. That means there's not a positive or negative. They're pretty much going to be very nice about sharing the electrons with one another. So one doesn't become more positive or negative than the other side. So because we talked about bonding as ionic or covalent, but really there's a continuum. You have ionic, and you have covalent, and if it's fair or even sharing, then it's said to be nonpolar. So this is sharing. Ionic again is stealing, right? So it's a theft involved going on. Definitely those electrons definitely have a positive and a negative for sure. And then there's a continuum. In here there is this polar covalent. Covalent means sharing, so it is sharing, but it's uneven. So we do get a positive and negative slightly. This is a definite positive and negative. This is a slight positive and negative because it's an uneven sharing. And we use these numbers. Now you do need to memorize these numbers, but honestly you could just memorize this one and know that polar covalent's in the middle. So that would be the easier thing to do. You'll see a couple questions like this on your test. Alright. So overall, we'll be picking up different elements, and you'll be telling me which one has the higher ionization energy, which one has the lower atomic radius. You can look on the homework page. You can see what kind of questions there are. Super easy. Trends are not hard. And here's the basics of what we got going on. Again, we're just doing these 3. So, and if you'll notice, radius is the only one that's different. It's the one that's down and to the left. The other 2 are up and to the right, except for this one is going to exclude the noble gases, right? Exclude the noble gases. So up and to the right, up and to the right, excluding noble gases for electronegativity. You also do need to know the definitions of these three words. Okay, hope this video helped. Come see me if you need me.